In this video, we're going to look at how to use substitution with definite integrals. Substitution will work exactly the same as it does with indefinite integrals, with one small caveat. When we use a substitution, we need to make sure to adjust the limits of integration to match the change in variables in the integrand. The substitution rule for definite integrals states that if u is equal to g of x, and f of x is continuous, just like in the indefinite integral case, then the definite integral from a to b of f of g of x times g prime of x dx is equal to the definite integral from g of a to g of b of f of u du. Notice that the function part here, the integrand, are exactly what they were in the indefinite integral case. The only difference here is that we are now adding on limits of integration. Notice that the numbers a and b here are actually values of x, because this is an integral with respect to the variable x. So a and b are x values. On the other hand, these numbers g of a and g of b are actually values of u, because we have an integral here with the variable u. And so in order to find the new limits, what we need to do is take the original limits a and b and plug them into the function g to get the corresponding limits in our new integral. In this example, we want to evaluate the definite integral from 0 to 1 of x squared times 1 plus 2x cubed to the fifth dx. To start, we're going to go through the standard substitution process by letting u be the inside function of our composition, 1 plus 2x cubed, and du will be the derivative of that function, which will be 6x squared dx. Now we notice that we only have an x squared dx here, so we're missing that factor of 6. So we'll divide by it so that we have du over 6 is equal to x squared dx, so that we can substitute that in directly. Now, if we were doing just an indefinite integral, this would be enough to complete the process, but we do need to account for the limits of integration here since we have a definite integral. And so what we need to do is we need to find the u values that correspond to each of our x values, which are 0 and 1, the two limits that were given in our original integral. And to do that, we're going to use this equation that we started for u, that u is 1 plus 2x cubed. And so when x is equal to 0, we know that u is going to equal 1 plus 2 times 0 cubed, or in other words, u equals 1. And when x is 1, plugging that into the equation for u, we see that u is going to be 1 plus 2 times 1 cubed, or u is equal to 3. And so when we want to then have these as our new limits of integration, 1 and 3. And so our integral becomes the integral, instead of 0 to 1, will be the integral 1 to 3 of u to the fifth power times du over 6. And so we've changed both our limits of integration. We've replaced 1 plus 2x cubed with u, and we've replaced x squared dx with du over 6. And we can now integrate this integral in a straightforward fashion. We're going to have 1/6 integral from 1 to 3 of u to the fifth du. When we find an antiderivative of u to the fifth, we're going to get u to the sixth over 6. And we want to evaluate that from 1 to 3. And so substituting 3 into the expression, we see that we get 3 to the 6th power over 36 minus 1 to the 6th power, which is just 1 over 36. And computing out all of this and doing the appropriate arithmetic, we see that we get a final value of 182 over 9. So this will be the value of the definite integral of x squared times 1 plus 2x cubed to the fifth power from 0 to 1. If you'd like to try a similar example, pause the video and try to evaluate the integral from 0 to pi over 2 of e to the sine of x times cosine x dx. The solution will appear in a few seconds. So here we have an inside function sine of x that's sitting inside the function e to the x, and so u will be sine of x. Its derivative is cosine x, which is the other factor of our integrand, and so our substitution works here perfectly without any kind of adjustments. We do have to adjust the limits of integration. When x is equal to 0, the lower limit, u will be the sine of 0, which is 0. And when x is pi over 2, which is the upper limit of our original integral, u will be the sine of pi over 2, or u is equal to 1. And so substituting these values into our given integral, we obtain the definite integral from 0 to 1 of e to the u du. The antiderivative of e to the u is itself e to the u, and we evaluate that from 0 to 1. And so we get the expression e to the first power minus e to the 0 power, which is just e minus 1, recalling that anything to the 0 power is equal to 1.